In this lecture, we will be proving the theorem that a symmetric positive definite matrix has a symmetric positive definite inverse. Let's remind ourselves of the definition of positive definiteness. A matrix A in Rn by n is positive definite if X transpose AX is positive for all vectors X in Rn such that X is not the zero vector. The other definition we need is that a matrix A is symmetric if A equals its transpose. So that means if you switch the rows and the columns of the matrix A, you recover the original matrix A. The theorem we want to prove is the following. Suppose the matrix A in Rn by n is symmetric positive definite, then A inverse is also symmetric positive definite. One thing implicit in this statement is that if A is symmetric positive definite, remember we abbreviate that SPD, then A is non-singular or invertible. So this is another theorem for symmetric positive definite matrices, which we will be assuming we can use. So first, let's deal with the issue of symmetry. So since A is invertible, we know that its inverse exists. And what does it mean for a matrix A to have an inverse A inverse? Well, we know by definition that A times A inverse is equal to the identity matrix, which is the n by n matrix that has ones on the main diagonal and zeros everywhere else. We can then take the transpose of both sides and we know, of course, that the identity matrix is symmetric. It is equal to its own transpose. Again, remember that the identity is this matrix of all ones along the main diagonal and zeros off the main diagonal. So if you swap the rows and the columns, you recover the original identity matrix. And so we have this equality here. But we know the rules for distributing transpose. We distribute the transpose to these terms in this product and reverse the order of multiplication. So we get A inverse transpose times A transpose is equal to the identity matrix. Now recall that A is symmetric, which means by symmetry we can replace A with A transpose. Now, note that we can multiply both sides on the right by A inverse. So we have A inverse transpose times A equal to the identity, and we can multiply on the right by A inverse. Of course, A times A inverse is the identity. And so this tells us that A inverse transpose is equal to A inverse because of course the identity times A inverse is A inverse. And this is what we wanted to show. So this tells us that A inverse is symmetric. As a result, we will often write for shorthand A inverse transpose as A minus T superscript. So this is just a shorthand that we often use. So this takes care of the first part of the proof. This proves that A inverse is in fact symmetric. We now want to prove that A inverse is positive definite. And so we want to show the following. For a given x in Rn that is non-zero, we want to show that x transpose A inverse x is positive. So this is our goal. Okay, so first we let x be such a vector in Rn. And let's look at x transpose A inverse x. We can insert a matrix product in here. Let's insert A inverse times A. And then we have A inverse x. We of course know that A inverse times A is the identity matrix from the definition of matrix inverse. And we can now use associativity of matrix multiplication to pair these off as follows. X transpose A inverse, that will be one term. Then we're left with that A in the middle. And then we have A inverse x. And let's note that because A inverse is invertible and x is non-zero, we know that A inverse x is also a non-zero vector. Essentially, the null space of A inverse consists of only the zero vector. Since x is non-zero, A inverse x thus cannot be zero. And let's give this a new name. Let's call this vector y. So we know that this vector y is non-zero by invertibility of A inverse. And this is coming from there's a classical theorem that you usually see in a first course in linear algebra. And you look at all the different equivalent conditions for a matrix to be invertible. One of those conditions is that its null space consists of only the zero vector. So if you multiply an invertible matrix, if you multiply on the left a non-zero vector here, you get a non-zero vector. So along these lines, we have renamed this A inverse x vector to be y, which we also know is non-zero. Now, let's also notice what happens if we take y transpose. So y transpose is the transpose of the product A inverse x. And recall, the way we distribute the transpose to this product is we take both transposes and reverse the order. And so we get x transpose A inverse transpose. But recall, from the previous part of the theorem, A inverse is symmetric. So this becomes x transpose A inverse. Again, by symmetry of A inverse. But notice that this is what appears on the left here. And so this term here is y transpose. Thus, this quadratic form that we started with can be written as y transpose A y. And remember, y is non-zero, which means this must be positive. Again, because y is not the zero vector, and we haven't used this yet, A is positive definite. Thus we have proved our goal. We started with an arbitrary non-zero vector in Rn, and we showed that the quadratic form with that vector and A inverse has to be positive, which is the definition of A inverse being positive definite. So this concludes the proof that A inverse is positive definite. And we see we have our theorem proved that if you have an n by n symmetric positive definite matrix A, its inverse is also symmetric positive definite. This is a handy proof to go through because it is kind of well representative of the type of proof that you construct, at least many of the proofs that you construct when you work with positive definite matrices.